Hello everyone, welcome back to the Inflection Point, and we are doing the AP Calculus course. In the last video, we gave some intuitive idea behind the concept of limits, and there were two intuitions which gave rise to the concept of limits, which were tangent problem and the area problem. Now for the exam point of view, let us discuss what are limits and how to solve problems which involves limits. So in order to understand limits, I give you an analogy. That analogy is that suppose we have a car, a motor car, and its maximum speed is, let us say, 200 kilometers per hour. Okay, so it is 200 kilometers per hour. Now, seldom it occurs that we reach this 200 kilometer per hour. We may reach 180 kilometer, we may reach 185, 189, 190, or even 195. But it doesn't happen that we exactly reach at 200 km per hour. So the point is, the concept of limit is, if I talk in the terms of speed, that this 200 km per hour is the limiting speed or limiting velocity of the speed of the car. We don't actually reach at 200 km per hour, but we know the performance of the car that yes, maximum it can reach 200 km per hour. So limiting speed of the car, limiting maximum speed of the car is 200. Okay. So in the same way, if we want to find out the behavior of the function at a particular point, but we do not know actually or exactly the value of the function, but we know how the function behaves, to what value the function approaches to as we move closer to a certain point. Right. So let us say we have a function by let fx is equal to x square, and the graph of this is something like this. This is my y-axis, this is the x-axis, so it touches the x-axis at origin, and suppose we need to reach at point x equal to 2. I mean, we need to find out the behavior of the function as x approaches to 2. Okay. So in order to reach at point x equal to 2, there are two directions. One direction is from left. That means I can reach this point 2 from the left direction, and also there is second direction that I can reach to this point 2 from the right direction, and just see to what value the function approaches. And this is what limit is. Limit, as the name suggests, is the limiting value of the function as we move closer and closer to a certain x value, right? Remember, it is different from the value of the function at point x equal to 2. We are interested in finding out to what value it approaches, right? So in simple words, limit is this only, right? So for example, in this case, if let us say I take point x equal to 1.9, okay, so here is the value 1.9, which is closer to the point x equal to 2. Here it is 1.9. So the value of the function it is approaching to is 1.9 square, and 1.9 square obviously is closer to 2, closer to 4, but it is less than 4. So it will be something like 3.9 something or 8 something. I do not know the exact value, but the point is it is closer to the value 4. Right. Similarly, if I put a point closer to point 2 but from the right, so a point which is just greater than 0.2, let us take 2.01. So if I put f of 2.01, right, so it will give me 2.01, sorry, 2.01. So it will give me the value of 2.01 whole square, which is again will be closer to 2, but it is slightly greater than 4. Closer to 4, but it is slightly greater than 4. So 4 point anything 0 point, let us say 2 something, right? So the point is, as we move closer and closer to point 2, moving from left or moving from right, I'm moving closer to point 4. So mathematically, I will say that the limiting value of the function as x approaches to 2 is 4. So mathematically, if I have to write this down, I can write this as value of the function fx, and what value we are interested. There is a symbol which is sometimes written as LT, which stands for limit, and sometimes we also write this as LIM. Okay, so I often use LT. So LT stands for limit. So limit of the function fx, and to what value we are approaching? We are moving closer to point 2. So this is written by x with an arrow 2. So this means it means tends to. So we pronounce it like this, that x tends to 2. What is the value of function as x tending to 2? So, or x approaches to 2. Okay, so this is exactly, again I am repeating that this is not the value of the function at x equal to 2, but in the neighborhood values of x equal to 2, right? So limiting value is coming out to be 4, right? It will be, it is slightly confusing that since the value of the function is 4, how the limiting value is also coming out to be 4, and that is the point. If limit both moving from right hand side or moving from left direction, if both the values are coming out to be equal, we say limit exists, right? And then the value of the function also comes to be equal to these values, to these limiting values, we say the function is continuous, right? And this we will deal with the topic which is continuity, but for now, and hence the function here is continuous, there is no break in the graph. That's why the limiting value and the value of the function both are coming out to be 4, right? You will understand this concept when we'll do continuity, how these two values are coming out to be 0, and then only we are in a position to say that the function are continuous. Okay, so I give you another example. Let us say that the graph is of a function is something like this. So it is increasing like this, and then after x equal to, let us say this point is a, this is fx, and it is coming out to be an open circle. I mean the value of the function at x equal to a is not, let us say this is b, but it is at c, right? So just after x equal to a point, the function is behaving like this, it is decreasing. Okay, so this is the graph of the function. Now if I need to find out the limiting value of the function at x equal to a, right? So what limit says, since I do not know actually if I give the definition of this function by in the terms of x and y, so I won't be able to see the behavior of the graph. So graph plays an important role in understanding the behavior of the function, right? So here this graph is just for the sake of understanding the behavior of the function and just for the sake of understanding the limits. Okay, so if I know the value of the if I know the graph of the function, so as I move from left direction towards x equal to a, the function gives me, I will say that the function is approaching to the value b, as it is clear from the graph. Okay, so mathematically I can say that left hand limit, the limiting value from left is known as left hand limit. Left hand limit, in short it is written as LHL. So the limiting value of the function is approaching to from left, denoted by LHL, is b. Mathematically I will write this as LT stands for limit, and x is approaching towards the point a but from left direction, and this left direction is indicated by a negative sign in the superscript of a. So this a minus is not equal to minus a, first thing. It is rather a minus 1, meaning it is just saying that I am moving from the left direction towards the point a. So this a minus is a value which is slightly less than a. Okay, so this is the limiting limit of when x tends to a minus, meaning the left hand limit of the function fx. Okay, so if I am writing LHL, mathematically it is written as limit x tends to a minus of the function fx, and from the graph I can see that the limit or the value to which it approaches is b. Now if I move from the right direction towards the point a, you will see that the function value is at c. Okay, it is not at b. So my right hand side limit, or RHL, this is called right hand limit, right? So this is your right hand limit RHL, and it is also coming out, it is not also, it is coming out to be C. Mathematically, it is LT when x tends to A. Now, since I'm moving from right direction towards a value which is slightly greater than point A, so that greater value to point A is denoted by A plus. Just like A minus was slightly less than A plus is slightly greater than A. And then Fx. So this is the notation for writing RHL, and it is coming out to be C. Right? So this is the, as now you can see here that left hand limit is coming out to be B, right is coming out to be C. So these two limits are not equal. And if the limit of the graph is not equal, that means there is a break in the graph. As you can see in the graph, that at point x equal to A, just before x equal to A, the function was approaching to B, and after x equal to A, the function is approaching to point C. And you can see here that there is a break in a graph. So limits just are a method which tells you or which gives you an idea whether there is a break in the graph or not. Right? So this is one type of break in which the value of the function at x equal to A is jumped to the value C. There can be other graph also that this value of this function at point A can be defined to be equal to B, meaning the second type of graph can be like this also, that it is at B now, the solid filled circle at B and then open circle at point C. So again the limit, left hand limit will come out to be B, right hand limit will come out to be C, but this time the value of the function is below C, or you can say at B. But as far as the concept of limit is concerned, both the limits are not equal. So when the limits of the functions are not equal, then we say the limit does not exist. Right? Meaning we are not in a position to tell anything that to which value the function is approaching. Okay, so we can say that if left hand limit is not equal to right hand limit, then limit does not exist. In simple words, in other words, as I said, we cannot predict to what value the function is approaching. Okay, because there is a break in the graph, and you can consider this graph or the limiting concept. You can understand the concept of limits just by assuming that there is a mountain. Okay, so there is a break in the mountain, someone is climbing on this side and someone is climbing from the opposite side, and both these P and C, both the persons, they cannot meet because there is a gap in the mountain. Okay, and that gap is huge. These two values cannot be made equal, and this is vertical. Okay, if you want to put a mud at point B here, you cannot put. Okay, it will fall because it is exactly above this point. Okay, so due to gravity, all the mud will fall. So you cannot fill this gap. Okay, until unless you fill horizontally, which does not seem to be practical. Okay, so this is the first case in which we can say that limit does not exist. Let us consider the second case also. Suppose we have a function like this. This is point A, or I should take the value as this is 2, this is 3, and then this is 4. Not 3, this is 3 only. Like this. This is 4, and let us say this is 3. Okay, Now consider this function. The question is whether limit exists or not. We have here 2, 3, and let us consider this point also, which is 4. Okay. If I say that find out the limit when x tends to 3 of fx. When we say x tends to 3, it combines both left hand limit and right hand limit. Right? Meaning we need to find out separately left hand and right hand limit, and if these two are equal, we can say that limit exists, and that limiting value can we can write as limit fx when x tends to 3 without any negative or positive sign. Okay. So limit of fx when x tends to 3, meaning for that we need to first find out the left hand limit. From the diagram we can see here that as we are moving closer to point C from left direction, the function is approaching to is 3. So left hand limit is just 3. Right? What about the right hand limit? So as I'm moving from right closer to point C, point 3, again the function is approaching to point 3. Please remember, we are not finding out the value of the function at x equal to 3. Okay, it is not defined at x equal to 3. It is defined, but it is at 4. There is a break in the graph, but that break is slightly a hole in it. It is not that the two mountains are different. There is a single mountain, but there is a hole in it, a crater type. Okay. So you can see here that x equal to 3, RHL is also equal to 3, and when these two limits are equal, we say that limit exists. Right? But what about if I need to find out limit when x tends to 2 minus? Okay. So when x tends to 2 minus, meaning I'm talking about the portion of the graph which is towards left of 2. And as you can see here that towards left of 2 the function is not defined. There is no function here. So if the function is not defined at any point, then also this is a second case when the limit we can say that limit does not exist. Okay. So for this case I can say that limit does not exist, or in short I can write DNE. Again I am repeating why this is DNE, because the portion which is towards left of 2, why toward left of 2? Because it is asking for 2 minus. Right. So if we need to find out the limit at point x equal to 2, I can only find out the right hand side limit, not the left hand side. Right. So these left hand side limit, right hand side limit, these are called one-sided limits. One-sided limits. So if one-sided limits at a point both are equal, then we say that limit exists. So at point x equal to 2, there is no left hand limit because it does not exist. So can we say that at x equal to 2 limit exists? It's an incorrect statement. Correct statement will be that only the right hand limit exists, left hand limit does not exist because the function is not there or the function is not defined. Okay. So if at a point if limit does not exist, right? So what are those conditions? That when left hand limit or the function is not defined, or when left hand limit is not equal to right hand limit, that means the limit does not exist. And the third case is when limit comes out to be infinite. Okay. For example, if the graph is like this is the graph of log x. So when x is 0, okay, if I need to find out limit when x tends to 0 and 0 plus, of course, because for x less than 0, log x is not defined. So this x should be in the domain, means function has to be defined. So here the limiting value for the function, as you can see from the graph, as I'm moving from right, it is going in the negative direction and it is going in the towards infinity. So when limit of any function at any point comes out to be infinite, we say that limit does not exist. Why we say limit does not exist? Because infinity is not a number. It is a very big number, of course, but we don't have any method to count or to measure that or to represent limiting. I mean, this sign of infinity is just to represent a big quantity. What exactly that quantity is, we do not know, right? So this infinite is not something that 1 billion or 100 billion or billion. Okay, if you again if you are saying billion, then again there is more billions after that. Okay, so it's a big quantity which we cannot measure. So it is just a tool to represent that big quantity. What exactly that quantity is, we do not know. Hence, we say that limit does not exist. Okay, fine. So this is all about the limits. So let me enumerate the points or the conditions when limit does not exist. For limit to not exist. So number one point is that if at x equal to a, for example, fx is not defined, not at x equal to a, I should write that if only function is not defined. Okay, it's not about that at x equal to a, there must be a value of the function. Okay, so if the function is not defined, meaning there is no portion of the function which exists. So we are not in a position to say anything, right? So if fx is not defined at a point, and second, if LHL is not equal to RHL, and third, if either of LHL or RHL comes out to be infinite. If any limit comes out to be infinite, that means limit does not exist. Okay, so this is the formal definition of the function of the limit that assumes that fx is defined for all x in an open interval containing c. So this c is basically at a point at which we are finding out the limits, but not necessarily at c itself. Okay, so we say that limit of fx at x approaches to a certain value c, it is equal to capital L, which is the limiting value, if the difference between these two, if the difference between the actual value of the fx and this limiting value, it is become arbitrarily small as we move closer to a point c. So you keep moving closer to a certain point, so that the difference between the actual value of the function and the limiting value of the function, it is very small, it is almost negligible. Then we can say that the limit or L is the limit of that, right? So in the previous example, suppose the function is approaching to a point 2 also at a certain point, let us say 2.5. So I cannot say that the limiting value as we are moving towards c, the limit is 2. No, there is again a scope between 2.5 and 3 to get closer to 0.3. Okay, so there is a scope of improvement to 0.2, right, to this value 2. So I can move closer to 3, means I can make this 2.5 even closer or more greater, such as 2.9999, so that the difference between the actual value, which is coming out to be 3 here, and the limiting value, it is very less. Okay, so this is the formal definition of the limit. You can read it afterwards, but concept wise I have explained it. One-sided limits and two-sided we have already done. Okay, so let us do some quick examples. So for the function in the given below, find the one-sided and two-sided limits at x equal to a if they exist. As you can see here, quickly, left hand limit is coming out to be 1. I am moving towards point a from left, so LHL is 1, RHL is coming out to be 3. So left hand limit and right hand limit for this part, and this part does not exist. Although all the three type of functions are different in the sense, you can see here that value of the function at x equal to a here is 2, here it is 1, and here it is not defined at x equal to a, right? So in all the three cases, limit does not exist because clearly there is a break in the graph. Just remember that mountain thing. Second example, for the function f graphed in the academic figure, find the limit of fx for 0 minus. So 0 minus meaning at x equal to 0, we need to find out the LHL. Okay, so 0 is here. slightly towards left of 0, I am moving towards point 1. So this is 1. Okay. At x equal to 1, value of the function is not defined. I mean, it is not 1, rather it is -2. But this is the limiting value to what value this graph is approaching as I'm moving towards 0 from left. That's the thing. That's the thing. Okay. For 0 plus, it is -infinity. Limiting value is -infinity. So either you can write infinity, or also, to be exact, I should write does not exist. Limit for fx when x tends to 0, again does not exist, because left hand and right hand are not equal. And value of the function at f equal to 0, it is defined as -2. So this is -2. Next one. Investigate the one-sided limits graphically. First part, as you know, the graph of y is equal to 1 over x is something like this. Okay, it's a rectangular hyperbola. And if I need to plot this x minus 2, I just need to transfer the y-axis to 2 units towards left. Y-axis, I'm not saying the graph. Okay, graph I need to move towards right by 2 units. Okay, so if it's one and the same thing, that if I transfer the y-axis 2 units towards left, so this is your y. And what is this? This is actually the asymptote which occurs at x equal to 2. Okay, so this is x equal to 2. Now as you can see here clearly, as I am moving from left hand side towards point 2, LHL is minus infinite, RHL is plus infinite, so this does not exist. For 1 by x square graph, whatever the portion of this which is lying towards left hand towards below x-axis, it will be above x-axis. I mean 1 upon x square cannot be negative, and at x equal to 0 function is not defined, so it will be like this. And both left hand limit it is going towards plus infinity, RHL is again going plus infinity, but again value is very big, right? But these two are not equal. We cannot equate infinity with infinity, so we cannot say that LHL is equal to RHL. So I should again write this as does not exist. And for log x also, I've explained it earlier in the example. Next, this will again help you to clear the concepts. So limit for fx when x is -1 plus, so here it is -1, and it is asking for right hand limit -1 plus, so limiting value is +1, so answer is true. B part, for 0 minus, this is 0 and minus, so slightly towards left of 0, function is approaching to point 0, so it is 0, so it is true. 0 minus, is it 1? No. 0 minus is actually 0, which we have done earlier. Okay. Next is it equal? No, these are not equal. 0 minus and 0 plus, yes, they are equal, although 0 minus is 0, 0 plus is 0. 0 plus, you can see here, RHL, it is coming out to be 0. So again, it is true. Limit exists? Yes, because both the limits are equal. Both one-sided limits are equal at a point. Limit exists. Value of limiting value of x equal to 0 fx? Yes. Okay, true. Is it 1? False. Now come to point x equal to 1. Value of the function at x equal to 1 as extends to 1, sorry. Is it 1? No. As I am moving towards 1, you can see here that left hand limit is 1, but right hand limit is 0. So at x equal to 1, there is a break in the graph, and whenever there is a break in the graph, both the limits won't be equal. Hence, limit does not exist. So had it been 1 minus, then it would be correct. So this is false. Is it 0? This is again false, right? So 2 minus, function is approaching to 2. No, again it is false. -1 minus, so -1 minus does not exist. Yes, this is true. If I'm going fast, let me repeat it. It says -1, so left hand limit at point -1. Here it is -1. RHL was coming out to be 1. This was true, but before -1 there is no function defined. And remember, there were three conditions when we can say that the limit does not exist. Since function is not defined before -1, so limit does not exist, hence it is true. And for 2 plus, here it is 2 plus, function is not defined. I cannot say that this will keep on extending like this on the x-axis. No. Okay. So there is no definition of the function after 2. So this is false. So true statement will be the limit does not exist. Alright, so that's all for the limits. I think you have enjoyed the video. Please like, share and comment. If you need any help in AP Calculus, please do comment. See you soon.